Hello everyone, welcome to the electromechanical devices course. In this video, we're gonna start a new topic, which is the operational amplifier. Amplifiers in general, we do have so many different types of amplifiers. These are one of the types of one of the electrical elements that give control to the current and the voltage through the electrical circuit. Using these amplifiers, we can do lots of things, and it is very useful when it comes to the electrical circuits and their implementation for electrical and electronic applications. So before we go deeply through the operational amplifiers, which is the main objective of this part, let us understand what does it mean amplifier in general, and let us fix here some basic concepts related to the amplifiers. So generally, amplifiers are used mainly to increase the magnitude of electrical signals. Like if you already have an electrical signal, like as we discussed before through chapter 4 and chapter 5, that if we consider like a sinusoidal input, like you have a signal with the sinusoidal form, and for some reason that this is like an input signal, V input, to a certain electrical element or electrical circuit, but unfortunately that this input signal, it is too weak or in other words, it has a very short or a very small amplitude, that this device or this electrical circuit won't gonna able to sense this input signal. So we have to put something here in between so we can do like magnification of this signal. We're gonna increase the amplitude of the signal. This is the basic idea of the amplifier. So amplifiers generally are used to increase the magnitudes of electrical signals so we can send them, we can make use of them. Because as I mentioned, if we are already delivering this input signal to an electrical component or element or whatever, but that the operating limit of voltage needed for this one, it is with a certain value, that this input voltage is too small in comparison to the required voltage needed to operate this electrical element. So we have to do magnification for it. We have to increase its amplitude so we can make use of it. This is the basic idea of the amplifier, is just to put here in the middle, we're just gonna add amplifier. We're gonna use an amplifier. The basic idea of the amplifier is to increase the amplitude of the signal, as we said. But some of the amplifiers actually would be used for decreasing the amplitude. It is not necessary to give increase in the amplitude. This is the common thing, and in the usual use of these amplifiers, we're usually increasing the amplitude, but for some cases we may decrease the amplitude. So generally we can say the amplifiers are used to adjust the amplitudes of input signals, of electrical signals, so we can make use of them. This is the basic idea of the amplifier. And this electrical signal, definitely it would be in the form of in the form of voltage. It is not necessary to be voltage, it would be like input current, like we do have, as long as we do have like voltage source and current source. So definitely the input for the amplifier or the electrical signal, it would be in the form as voltage as a function of time, or current as a function of time. So if we do have this signal and we would like to adjust this signal, we can do it using the amplifier. This is the basic idea of the amplifiers. So a typical example to this case, for example, as mechanical engineers, if we're going to talk about the strain gauges. The strain gauge is one of the devices that we are using to detect the strain, or to measure the strain induced in a material sample up on the or during the tensile test. Like when we fix a sample, a material sample in a tensile testing machine, assume that this is the sample and it is like kind of fixed from both sides, and we just stretching this material from both sides as already shown here, this direction and this direction. So what we do, we fix here in the middle a strain gauge. So this is the strain gauge. The strain gauge, this is like a sensor, like measures something that is gonna measure this the stretch in this material sample. But basically the amount of stretch over this small portion of the sample, it is very small. It is, so it gives, like you could say that this sensor, it gives or delivers, provide a signal, electrical signal, which is very small with very small amplitude, that is barely can be seen or observed by the machine, the machine control unit or the mother unit of the machine itself. So we have to do like magnification of this very small signal so we can make use of it and we can detect the frequency properly, and this is what we need through the amplifier. So in this case, that the signal that already delivered or generated through this amplifier, this string gauge, it gives a signal. This signal is too small with a small amplitude, so we have to apply here an amplifier. The amplifier is going to increase the amplitude of the signal so we can send this signal. This is the basic idea of the amplifier, even in how we are using it for the tensile test of the machine. And there are lots of other applications that would be used that basically we are using these amplifiers for. So this is the concept of the amplifier, and now what we're going to do, we're just going to go over these amplifiers with more detail in terms of based on the electrical concept. And definitely there is another course that you're going to consider these amplifiers for, which is the dynamical systems and their control. This in the senior level you're gonna study this course. So but here we're gonna consider this amplifier from their like their operating principle, how they are working, what are the different components, how we can consider this amplifier from the electrical circuits point of view, and how we can do even to electrical circuit that include these amplifier. This is going to be the objective of this part. Especially we're going to consider these operational amplifier. So now let us discuss the ideal case, or let us see the ideal case of the amplifier. In the ideal case, like if we assume that this is the amplifier, and as I said, we do have bunch, we do have so many different types of amplifiers. The one that we're gonna focus on is the operational amplifier. Operational amplifier is just one of the types of the amplifiers. So assume that this is the input signal. This signal, it would be a current or a volt. In this case, we are assuming that there is input voltage source, or there is input voltage signal that already delivered through the amplifier and is going to be the output. The output here, it would be any machine or anything. It would be a machine, it would be lamp, it would be anything, it would be even another electrical circuit. So this RL, this is the resistance over that needed to attract. We said that once before at the start of this class, you have to deal with this resistance like something that is gonna attract the current to pass through it. Okay, but if there is a branch with no resistance, there shouldn't be any current over this branch. So that's why if to have a machine here operating, this machine, it should attract some electrical energy, and to attract and to give this machine ability to attract some electrical elements so it can work, it should have some specific resistance. So assume that we have this machine or something here like a machine, for example, as I mentioned here, and we already delivering a signal directly to this machine. The machine won't gonna able to sense it because the signal is too short amplitude, or is too weak signal. So we have to do like magnification and amplification of this signal through amplifier. So the signal is gonna proceed through the amplifier, so it will be magnified or it would be changing. So what are the changes that we are expected in this signal? We do have, if we already, this is the input signal wave, this is the input one. So any wave signal like sinusoidal form, it should have amplitude, which is the maximum height. This is the amplitude of the signal, right? It should have amplitude value. In addition, it should have like so this is the amplitude. In addition, it should have like a wavelength. And definitely the wavelength there is, or this is the periodic time, because this is the time here, so this should be the periodic time, and it should have like a wavelength. In addition, it should have a frequency, and we said that this frequency, the speed of changing this wave, like completing one cycle per unit time, or the time needed, the periodic time, this is the time needed for completing one cycle. So, but if this is the input signal, this is V input, and definitely this is going to be the output after the amplification. So the amplifier should do something, should do changes to this signal. So changes, it would be in anything. It would be in the amplitude, it would be in the frequency, it would be in the periodic time, which definitely related to the frequency. So we are expecting any changes to any one of these parameters of the input signal. in the output form. So this is going to be the output signal, V output, right? But in the ideal case, here we are talking about the ideally an amplifier. In the ideal case, an ideal amplifier, that the change is going to be only for the magnitude. Like an amplifier produces an output signal with identical wave shape. The wave shape is the same. It is sinusoidal small wave shape, so it's going to be the same shape as the input signal, but with a larger amplitude. The change is going to be in the amplitude, and in many of the cases, the frequency is going to be the same. But if here we are talking about the ideal case, the ideal amplifier, I know that this ideal case, it is not, you know, like the perfect case, and it would be hard to achieve 100% ideal situation, that there is no change in the frequency, and the only change that we're gonna get through the change in the amplitude. But this is the ideal case, and we can assume that, and this is what we're gonna depend on, and we're gonna assume in the in this part. So if this is VI, this is the input voltage, this is the input signal, and remember that this signal here, it is voltage, that we can change this signal to be current, and instead of being volt it would be current, so we're gonna have the same formula. And this is the output, this is the output signal, and definitely here this is the gain of the amplifier. This is known as the gain of the amplifier, and we are adding the subscript here V, indicating that this is voltage gain, that this gain is associated with the gain for the voltage for a voltage signal. So this equation, this is, it's going to be the shape of the, or the changes in the output voltage up on using amplifier. Like the KI there, we're going to have the same shape, but only difference, we are increasing the amplitude of the amplifier by a factor. This factor is known as the gain of the amplifier. So the gain of this is the factor by which we are increasing the amplitude of the input signal through the amplifier, keeping the frequency the same. And this gain, it should be a constant value. It is not a function of time. The only thing that should be functions of time are the signal themselves. So AV, this is the voltage gain, and any amplifier it has its own gain. So this is like a characteristic property of the amplifier itself, and it would be different definitely from one amplifier to the other. The voltage gain is usually larger than 1, as long as we are interested in increasing the amplitude, as I said. But in some cases, if we would like to decrease the amplitude of the amplifier, so this AV, it should be, or the gain in general, which is A. So generally A, this is the gain of the amplifier. This is the amplifier's gain. If we said, for example, AV, we can say AV, this is mean that this is the amplifier, this is the amplifier. Also amplifier gain, but for, it is gain for voltage signals. And it would be like AI in case that we do have, this is the amplifier gain, but for current signals. Make sense? But anyway, you can just save A or add the subscripts for V and I to distinct it, whatever it is, voltage or current, it's up to you. So again, the gain itself, it would be bigger than 1, and in this case we are increasing the amplitude. But if it is less than 1, it means that we're already decreasing the amplitude of the signal. And also it would be negative, it would be positive. If it is negative, it means that we're gonna end up with inverting amplitude. This is gonna give inverted signal, and I'm gonna show you what does it mean, inverted signal. And if it is positive, it means that we do have non-inverting amplifier. So what does it mean this? For example, let us assume this input signal, assume that this is the signal that we have, this is the time t. If we consider this input signal, like this is like input voltage with this sign, with this wave, whatever this or this signal, and we're gonna use an amplifier. So the amplifier, it would be with a negative voltage gain, or it would be with a positive voltage gain. If it is with a negative, so it will be inverted. Inverted, it means it's gonna take the green shape. So this is the inverted signal. It's gonna be the same shape, but it looks like it had been mirrored. So this is the inverted version. Like if any positive value here, it will it will be consistent, or it will correspond to a negative value on the inverted version or after the amplifier. So this is the output voltage. It's gonna be inverted. Here it is non-inverted signal in this case. So this is in case that we do have the gain is positive, but here in case that we do have the gain is negative, it's gonna be inverted signal. So this is the key idea. What does it mean inverted or non-inverted? And for this case, if it has a negative, as I mentioned, this amplifier or the gain of the amplifier, it is a property of any amplifier. Like any specific amplifier, it has its own gain value. It is a constant value for the amplifier. If it is positive, it means that we do have non-inverting, or non-inverting amplifier. If it is negative, we're gonna have inverting amplifiers. Also, so generally, and we're gonna explain these two statements with more detail. An ideal voltage amplifier, it senses the voltage of the source and produces an amplified voltage across the load. What is the load? We said that this is like the machine that we are going to operate. So the ideal amplifier, it senses the voltage of the source and produces the amplifier voltage across the load that is independent of the load impedance. What is the load impedance? We discussed the impedance over chapter 4. Impedance, that we said that if we have a resistor or a capacitor or inductor, we can convert them into an equivalent resistance, but in the complex plane. This is the impedance. So if we assume that we do have here a machine that works with resistor and capacitor and inductor, so all of these different components, they do have impedances, then we can combine all of these impedance of these elements into one impedance, which is known as the equivalent impedance of these impedances within the machine itself. So this is gonna give us the load impedance. So in case that the converted output voltage does not depend on the input of the load impedance, and does not depend on the load impedance, this indicates an ideal amplifier. So the key condition of the ideal amplifier, that the output voltage or the output voltage does not depend on the load amplifier. This, what does it mean? The ideal amplifier, whatever for the voltage or the current. For an ideal current amplifier as well, it sends the current of the source and forces an amplitude current through the load that is independent of the load impedance as well, like in case that we are using the amplifier to sense and magnify or increase the amplitude of a current. We said that the input signal, it would be in the form of a voltage or a current, it depends. And the key idea for the ideal amplifier, that these signals, their output form of the signal does not depend on the load impedance. Let us move to another term here, which is the differential amplifier. So we said that amplifiers are different types. Some of these types are they can be classified as or known as differential amplifier. The differential amplifier, it has two input sources. This is one of the things, like this is the amplifier, and it's gonna work over not just one signal. No, the input is gonna be two signals, two different signals. Like we do have one signal wave and there is another signal wave, V input 1, V input 2, as already shown here in the figure, and these two signals, they shall be proceeding to the amplifier. The amplifier is going to do something and is going to give an output signal, right? So basically this depends on the amplifier itself. The type that we are going to discuss is the differential amplifier. In the differential amplifier, we should have here two terminals. One is positive and the second one terminal should be negative. The positive terminal, it gives or it deals with this input signal with non-inverting form. Like this signal, it won't gonna do any changes to this form except the amplitude, but it's gonna have the same shape and it is non-inverting, which is very similar to this case. We discuss here inverting and non-inverting. It means that with respect to this signal, the amplifier is going to be with a positive gain, but here it will be with a negative gain over this negative terminal. That's why we have here inverted input signal terminal, or the inverting input terminal will be, or this terminal will be inverting this signal, input signal. So given this amplifier with this specification, assume that even if we assume that this term is 0, if this input signal is 0, and we have just VI1, so, and this input signal will be proceeding here, and assume that the gain of the amplifier is just A. So what will be the output? According to this equation, on the top here, that the output signal should be the gain times the input signal, right? So the input signal here would have only one signal, which is VI input. VI input. So for the case V input 2 equals 0, so we do have only one signal, which is V input 1, so the V output, it definitely is going to be the gain, and the gain is going to be positive. And the gain is just a value, forget about it, it means it's going to be like a positive value. It deals with like a positive, but assume that this A is the gain of the amplifier, and since this signal is already moving or proceeding through the positive terminal, so it will be as it is, it won't gonna be converted. So this is gonna give us V input 1 times V input 1, which is already given here. But for the case, how about if we switch the situation? How about if we put this one will be with the value, but this VI1 will be 0. So the output signal will be A, the amplitude, times negative VI2. Why negative VI2? Which is gonna give us negative equals the negative of A times VI2. Why we are adding negative here? Because this VI2 will be inverted because of the negative terminal here. But how about for the case, how about here, for the case that both I1 and have a value, and VI2 and I1 both they do have values. So the V2 will be negative, but the V1 will be positive. So the output signal definitely will be the gain times V1 will be positive, but VI2 will be negative. So it's gonna be the difference between them, and that's why we do have the differential amplifier. The differential amplifier, it gives the output signal that depend on the difference between two input signals. This is one of the things. So here we do have like you already forming a special output signal from two given input signal. This is one of the types of the amplifier. So generally speaking, if we do have for any, this is for any two input signals. Assume that you do have two input signals, and these two input signals will be proceeding through the amplifier. So if these two input signals, which is VI1 and VI2, we can end up with another signal which depend on the difference between the two signals or the average of these two signals. So the difference between the two signals is known as the differential signal, and the average of these two signals is known as the common mode signal. So we can design an amplifier that gives us the common mode signal, or we can design a differential amplifier that gives, or amplifier that gives us the differential signal. So again, in general, if we do have amplifier and we do have two input signals, one is VI1, VI2. So there should be an output, V output here, right? So the V output, this output signal, it would be in one of these two forms. It would be like the differential signal, or it would be the common mode signal. This depends on the type of the amplifier in the middle here. Like we can use an amplifier, we can set up an amplifier here that gives us the average between these two input signals, or we can set up an amplifier in between here to give us the difference between these two signals. So this is gonna give us the I differential or the VI common. Make sense? In case that we set up an amplifier here that gives the differential signal, this amplifier is commonly known as the differential amplifier. So the talk here is on the differential amplifier. For an ideal differential amplifier, for the ideal case, this amplifier produces an output voltage that is proportional to the difference, depend on the difference between the input and the input voltages. Like you'd have two input voltages, and if the output signal, it depends on the difference between these two input signals, this type of amplifier is going to be definitely differential amplifier, and the constant of the proportionality relation here, it's going to be the gain of this amplifier. Make sense? So this is the basic idea of the differential amplifier. Remember that we may have another type of amplifier that would give us the common mode signal, but the focus here on the differential amplifier that gives us the differential or the signal, output signal, depending on the difference between the two input signals. And this is gonna be the general formula for the differential or the output voltage through a differential amplifier, that we do have VI1 negative VI2 and AD, which is the differential gain of the differential amplifier, which is just A. We said that this subscript we just added to give like a definition of the type of the amplifier or the type of the signal as AV or AI or AD as the differential gain, but generally it's just a constant A. Make sense? So this is the basic idea of the differential amplifier, and this is one of the types. So the question is why we are introducing these differential amplifier? Because the main objective here of this part is to discuss and to show you the operational amplifier, and these operational amplifiers, they already differential amplifiers. So that's why we have to define what does it mean a differential amplifier. So amplifiers would be with only single input and it's gonna give one output. We do have some types of amplifier that they take two inputs and they give one output. We do have some amplifier that they take two inputs and they give two outputs. We do have some amplifier that they take more than two inputs and they give more than one output. So this we do have bunch of types of amplifiers. The one that we're gonna focus on the operational amplifier, and the operational amplifier, it is differential amplifier. So what does it mean a differential amplifier? Generally it is amplifier with two inputs and gives one output. This is the differential amplifier, which is the operational, takes two inputs and gives one output. The output, it depends on the difference between the two input signals with a magnification factor known as A, which is the gain of the differential amplifier. Make sense? All right, so as for the operational amplifier, as we mentioned, it is one of the types, it is already differential amplifier. So the operational amplifier, it can be approximated like, or the abbreviation, it is OP amplifier. So this is like the abbreviation for operational amplifier. So for example, I'm pretty sure that some of you like have seen this amplifier before. So this should be the operational amplifier that we're gonna talk here about it. It is one of the essential components that is used in so many electrical circuit. It is, as I mentioned, it is the operational amplifier. It is a differential operator amplifier, and this amplifier, it should be with two inputs and only one output in this way. So that's why it has this triangular shape, that this form, once you see this symbol within an electrical circuit, you should understand that this is the operational amplifier that we are talking about. So it has like two terminals, two inputs. One is non-inverting input and the second one is inverting input with a negative sign and positive sign, and this is going to give us an output. And definitely because of the positive and negative, this output, it will be dependent on the difference between the two inputs. So that's why it is a differential amplifier. It has, so the operational amplifier it is a differential amplifier having both inverting and non-inverting terminals. So as we discussed before, in a operational amplifier, it would give two for any two input signals, we may have the difference between the signal. This is going to give us the differential signal or the common mode signal. For the operational amplifier and the ideal one, the common mode signal, it should be zero, or in other words, we're gonna say that the gain for the common mode signal, it should be zero, but the gain for the differential signal, it should be infinity. So what does it mean zero? It means that we don't need any common mode signal, so we have to cancel this signal. And this signal, since it depends on the average of the two input signals, so it means that this term, it should have a value, but it should be multiplied by a zero gain through the amplifier to cancel this signal. So we have to cancel this signal for the operational amplifier, and we should end up with just the differential signal, and this is the main function of the operational amplifier. For the ideal case, this should be zero. The gain of this signal should be 0, and the gain of this one, it should be infinity. What does it mean infinity? It means that we have to end up with all of this signal and nothing would be lost of this signal, and this in the ideal case gonna be achieved as long as the gain it tends to infinity. In the practical use of this amplifier, the differential signal, the gain for the differential signal, it is within this range, 10 to the power 5 up to 10 to the power 6. So that's why it is kind of tends to infinity. That's why this is the objective of the operational amplifier. So if you had been asked, for example, that the gain of the common mode signal of the operational amplifier, you should understand that the gain for the common mode signal, it should be tending to 0, but the gain for the differential signal, it should be tended to infinity. So we're gonna discuss these characteristics of the ideal amplifiers with more details, but I'm just gonna mention them very quick, then we're gonna demonstrate some points so we can understand what does it mean, these things. But generally, the general characteristics of ideal amplifier, this is the ideal case, this is the perfect case of the operational amplifier, that first of all, as I said, that it should have infinite input impedance. We do have like input impedance, and I'm gonna explain what is this input resistance or input impedance. It should be tends to infinity, and infinite gain for the differential signal. As we said, the differential signal, it should be the gain, it should tend to infinity, huge values, and this is one of the common characteristics of the operational amplifier. And zero gain for the common mode signal, because we have to get rid of the common mode signal and we shall end up with only the differential signal. Also, it should have zero output impedance. So these are the general characteristics of the ideal operational amplifier, and let us demonstrate these points over the next examples of these operational amplifier. First, we're going to consider the operational amplifier in the open loop configuration or open loop setup. Like, what does it mean? Open loop is an open loop system in general. This is the kind of the system that you're just gonna give input and then you're gonna receive output, and that's it. The other type is the closed loop signal, a loop system. Closed loop system, it means that you're gonna have like input, then you're gonna end up with an output, then there is a comparator that is gonna compare the output signal to the input signal again. So this is known as a feedback signal. This happens for closed loop systems or the closed loop or operational amplifier with closed loop configuration. Now let us consider the simplest configuration or setup of the operational amplifier, that it is like a open loop amplifier. For open loop amplifiers, this is gonna be the typical shape of the amplifier, schematic representation of the amplifier. Like, these are the two input signals, V1 and V2. As you can see, V2, it is negative, so it is already the negative. This is the inverted input and inverting input, and this is non-inverting input for the V1, as long as already over the positive terminal of the amplifier. And VID, this is the difference between this VID. It should be the difference between V1 is positive, negative V2 is already negative. So this is like the input voltage. This is VID, this is the input voltage for the operational amplifier, which depends on the difference between V1 and V2. Make sense? For example, for the case that V2 equals 0, so VID will be V1. In case that V1 equals 0, VID will be negative V2. Make sense? This is for, so if V1 equals 0, we're gonna have VID equals the negative of V2. And if in case that V2 is the one equals 0, so the differential input voltage to the amplifier will equal to the V1. This is the differential voltage to the amplifier. This is gonna be the input. You should understand that this is the input voltage. This is the input voltage to the amplifier. This is the voltage, this is the input, and then we're gonna end up with output. So V output, this is the output voltage that we are seeking. So we have to figure out how much is this V output in terms of V input. This depends on the gain. So if we assume that the gain of this amplifier is A, so we are expecting that V output, it should equal to, or let us use this color, that we are expecting to that V output, it should equal to the gain, which is A times VID, which is the differential input or the input differential signal to the amplifier, which depends on the difference as we defined up there. Make sense? So this is for these things in the beginning. So what is RI and RO? I stands for input. So this is the input impedance, or this is the input resistance. So we're gonna do this one with this one in general, like, because we said that the impedance in general, it works like a resistance, right? It is like equivalent resistance but in the complex domain. So we're gonna say that the RI, this is the input impedance that we just mentioned up there. This is the input impedance, where it is, yes, this is the input impedance, which should be R input. Make sense? So this is the input impedance, it should equal to, this is our input and our output. This R is the output impedance. Okay, this is the output impedance, which this one. Okay, for the ideal amplifier, this output impedance, this R output, it should be 0. I'm gonna let you know why 0, while the input impedance, it should be tending to infinity. So why we need R input tends to infinity? We need it to collect all of these two signals, or in other words, to collect the difference between all of the difference between V1 and V2. So what does it mean Ri tends to infinity? To collect all of this gain. For example, if we consider this loop, like this Kirchhoff voltage law loop, this one that it goes inside then it comes outside, and we apply Kirchhoff voltage law to this loop. So we're gonna have the VID, which is the difference here. It should equal, because there should be a current I, right, going through this loop. So it's gonna be I times R, right, which is R input. So in case that would have this R input, it is already 0. So there is no differential, or there is no input voltage that is gonna be delivered to the amplifier, kind of, right? So this is the basic idea of having, that's why we said that we should have a value. Infinity here, in the ideal case, R, it should be tending to infinity, but it is not necessary to have an infinite resistance. If you have any resistance, whatever it is acceptable, and for this case you're gonna collect the inputs. But as you are increasing this resistance, the efficiency by which this amplifier is going to receive or collect the difference between V1 and V2 is going to be increased, and is going to be much more efficient in collecting the difference between V1 and V2, as long as this R tends to infinity or increases, or with a bigger value. But the worst case is going to be that in case that we do have this R input, it is already 0. So in this case, it means that we are not collecting any inputs to the amplifier, or you could say that the amplifier, it won't gonna sense the difference between these two signals. Then it means that it won't gonna be able to do amplification or increase in the amplitude or magnification of this signal. Make sense? So that's why one of the characteristics of the ideal amplifier, that the input impedance, it should be like 10 to infinity. But for the output, how about the output? It should be 10 to 0. So why this one tends to 0? Because if there is resistance here in the output, at the output terminal or the output side of the amplifier, this R output is going to take part of the output of the total output signal or the total output voltage. For example, because it is already in series with this parallel. So if we consider this is like a loop, and I ask you to apply Kirchhoff voltage law to this equation, you're gonna find that the output, it should be R output times a certain current plus the V output, it should equal to the total output voltage, right? So it means that this amplifier can give a specific amount of output voltage, but there is an internal resistance. You should understand that this Ri and Ro, these are like kind of internal resistance of the amplifier. So the amplifier itself takes part of the total voltage that should be delivered to the machine. This is the machine that we're already operating, right, which is RL as we agreed. So it means that this means that some of this output voltage will be lost because of this RO. So that's why, but if in case that would have this RO already zero, so all the output voltage that is gonna be delivered by the or generated by the amplifier will be totally or entirely be used for the RL, which will be used, I mean, for operating the machine. And this is the ideal case and this is the best case. So that's why one of the specifications to judge whatever we do have an ideal amplifier or not, that this R output it should be zero. So that's why this explained, that's why one of the characteristics of the ideal amplifier that it should be with zero output. We already explained these 2 points. So we explained these two, and we explained these 2 points before on the top here. Like as we mentioned, that to have an ideal amplifier and the operation amplifier, it should be differential amplifier. So differential amplifier, it means that we should end up in the ideal case with only the differential signal, and we have to get rid of the common mode signal. And to do so, we should have infinite gain for the differential amplifier. Infinite gain, this is the ideal case, but in case that the gain it is high within this range, it is perfect to us. It is like tends to infinity, as we mentioned for the differential signal. The gain for the differential signal in operation, many of the operational amplifier, it should be within this range, 10 to the power 5 up to 10 to the power 6, and zero, and it should have the operational should have the zero gain for the common mode signal to get rid of this signal. These are the specifications of the ideal operational amplifier. Make sense? So now let us discuss different configurations of the operational amplifier, starting with the inverting operational amplifier in the open loop configuration. We still work over the open loop configuration. There should be input, and we're gonna end up with an output, and that's it. Here we do have this configuration. It is inverting operational amplifier. So for example, what is the difference between this one and this one? In this amplifier, the 2 terminals, there are 2 voltages already moving inside to the amplifier through these 2 terminals. Like we do have V1 and we do have V2. And the amplifier just collect the difference between V1 and V2 and deliver it to give it like an output, and that's it. But how about some of the operational amplifier? We can use them to just invert the form of an electrical signal with even increase or decrease in the amplitude, but it should be inverting in the meanwhile. So for example, for this operational amplifier, this V1 it has a certain signal, V2 it has a different other signal. It would be like square signal, for example. And this is like sinusoidal signal, V1 and V2. So the operational, what will be the shape of the signal of the output voltage? It will be different than these two. Why? Because I'm gonna collect the difference between these 2 signals, then I'm gonna give an output. So the output will be entirely different than the 2 input signals. Why? As long as these signals are of 2 different shapes. Make sense? But this is not practical. Most of the practical use of the operational amplifier, because we in many of the cases, even if you remember in chapter 5, we said that the electrical circuit, the current or the voltage will be with the same form, with the shape, with same shape, even with the same frequency, which is omega. We said that omega, it should be the same within the electrical circuit, right? So the practical use that these 2 signals, they should have the same form, even they should have the same frequency. So they kind of 2 identical signals. The difference is gonna be in a few things, like the difference in the amplitude, there would be a little bit difference in the frequency or the phase angle. So there is a small change or difference between these two signals. This is what practically what we are using the amplifiers for, right? So that is fine, kind of, to calculate the difference between V1 and V2 and assume that this difference, it will be delivered through only one terminal, and the other terminal there is no voltages, like this case. So what I've did here, that this is the total input signal. This total input signal, it should be the difference between V1 negative V2. V1 negative V2, and there is no voltage is gonna be delivered through this branch. It's gonna be identical to this case. So it is looks like you just calculated the difference between V1 and V2, and you deliver this difference through one branch, and you just put the other branch equal 0. You're still delivering the same differential signal that it should be delivered as input to the amplifier. Okay, so this is V input is gonna be the difference between V1 and V2, and there shouldn't be any voltage over the second branch. So this VID still equals the V1 negative V2, which should be the V input in this case. Or to be more accurate, in the total, there should be the difference V1 negative V2. Make sense? Then we're gonna have here like a kind of resistance over this branch to just generate some current to pass through the resistance, then it's gonna move through the operational amplifier to give an output. So again, the output is gonna be the gain times the input signal, but we do have here a negative sign. Why? Because this input is already delivered through a negative, the negative terminal. It means that, or inverted input, it means that this input will be magnified with the gain factor of the amplifier, so it's gonna give us an inverted form of the original form. Multiply times the gain, which is already A equals 1 or bigger, it depends. If it is 1, so it's just gonna convert the signal with the same amplitude. If it is bigger than 1, is going to increase the amplitude and invert the signal because of the negative here. So this is the type of the inverting operational amplifier in the open loop configuration. Make sense? Non-inverting, so for the non-inverting, the only difference that instead of delivering the input through the negative terminal, we're gonna deliver the input through the positive terminal, or simply you can just switch the amplifier positive and negative as we did here. Like instead, this is the input, which it should be the V1 negative V2 in the original configuration of the amplifier that we discussed before, and this should be the input current that is gonna pass through this R input. This is the input resistance that should be tends to infinity in the ideal situation, and this is the R input that should be tending to infinity in the ideal situation to collect all the input voltage to deliver it to the amplifier, and this is what we're already considering here. And but this terminal is the positive terminal, so that's why the gain is gonna be not the gain, the output signal, it will be positive with the same shape but with different amplitude depending on the gain of the amplifier. Make sense? So this is the basic idea of these two different configurations in the open loop. Something that you should understand here, how about if I decided to set up or write the loop closure equation to this loop? So within this loop, we can write or draw like a representative electrical circuit to this loop here. Like we do have an input signal, V input, and there is R input, and there should be a current I. This configuration, this electrical circuit is equivalent to this one. Like we just close this line because simply these are two grounds, right? So these are the two ends. It can be closed, no problem, right? So this is gonna be the equivalent representation to this loop, and the Kirchhoff voltage law to this loop is gonna give us the input voltage. It should be negative since it is an input, or we can say that the input and these two will be output. This is gonna be the VID within this loop. So plus the current, which is I times R input, plus the VID equals 0. This gonna give us the Kirchhoff voltage law to this electrical circuit. Keep this one in mind because we're gonna need it for a discussion later. For the non-inverting operation amplifier, it's gonna be the same, but here this is the Kirchhoff voltage law. It's gonna be the same thing. The input voltage, which is negative V input, and plus the I times R input. This is an input, and the this one is gonna be this is output. The voltage over this one over this resistance output, and this VID is gonna be output for this loop and input for the amplifier. So plus the VID equals 0. So this is gonna give us the Kirchhoff voltage law for this non-inverting operational amplifier. So all of these different amplifiers were represented in the open loop configuration. Like there is input and you're gonna end up with an output. How about if we decided to work in closed loop configuration? These amplifiers gives more control over the output signal in comparison to the input signal through a feedback signal or terminal here or branch which with a resistance as RF. This is, as we discussed before, this is a kind of closed loop system that it should have like a sensor that is gonna detect the output signal, then is going to compare. This is a like kind of comparator that is gonna compare the output signal to the input signal. This is the input signal that should be coming through this branch, and this is the output signal. So we just collect these two signals and we give like a feedback, whatever it is, with the same value or the suitable value or not. So this is kind of the like more advanced control system, and you're gonna study this control system in the senior course as I mentioned before. But anyway, we do have here a feedback. This branch is a feedback branch, so that's why we do have the subscript as F stands for feedback. And this is like one of these essential things to have a closed loop operation amplifier. Inverting or non-inverting operation amplifier in general with negative feedback like this one, or this is a typical example of inverting operation amplifier with a negative feedback. What does it mean, inverting operational amplifier? It means, as we mentioned before, as you can see, the input signal, it is going through the negative terminal of the amplifier, so that's why it is inverting operational amplifier with a negative feedback. So what is the feedback? The feedback, this is the branch of the feedback, and this branch is already connected over the negative terminal as well, so it is a negative feedback. But if I need a positive feedback, the positive feedback, it should be coming in this direction. So you could say that this is RF positive. All the operational amplifier that we already using, all of them, they are using negative feedback, and none of them is using a positive feedback. Why? Because the positive feedback gives instability in many of the cases, and that's why it is not recommended to have a positive feedback for the operational amplifier, and all the time we are using negative feedback to avoid the instability case for this operational amplifier in the current or the signal. Instability, it means that you're gonna end up with random and chaotic behavior on the output signal in case that we are using a positive feedback, right? So that's why all the time we're gonna use the negative feedback, and this is the common thing for this operational amplifier. Why it is negative feedback? Because it's already going over the negative signal as so shown here. And why it is inverting operational amplifier? Because the input is already comes or delivered through the negative terminal also of the operation amplifier. This is a non-inverting, this is an example of a non-inverting operation amplifier also with a negative feedback. Negative feedback, as you can see, the feedback is already coming through. This is the feedback signal coming over or through the negative terminal of the operation amplifier, but the input is already going through the positive amplifier or positive terminal. So that's why it is non-inverting operational amplifier with a negative feedback. This is the form how you're gonna see it as a negative feedback in this way. Make sense? So since this is positive, we are expecting this output signal with the same form in the same phase. It means that the same phase with different amplitude, only the difference is going to be in the amplitude, but it is not it is non-inverted signal. It's going to typical the same shape or as this input signal, but here the output signal is going to be of inverted form of the input signal, and this with an amplification factor or the gain depending on the gain of the amplifier itself. Make sense? So this is like in this introduction we give like introduction in this or in this video we give introduction about this amplifier, the concept of the amplifiers. Also we discussed the differential amplifiers, then we discussed the operational amplifier, and we said that these also are differential amplifiers, and we discussed the specifications or the character of the ideal amplifiers. Also we discussed different configurations and setups of this amplifier. The next meeting we're gonna know how we can do analysis to electrical circuit that include either inverting or non-inverting operational amplifier with negative feedback. So the main concern or the main focus is gonna be over this operational amplifier in the closed loop configuration, and all of them will be with negative feedback. And we mentioned the reason, because that the positive feedback would achieve some instability in the output signal, so that's why it is not practically recommended. All the time it is recommended to have a negative feedback, and this negative feedback is going to give us more control over the output signal, as we're going to see through the next video. So in the next video we're gonna know how we can do analysis to the electrical circuit that include operational amplifier. Nothing won't gonna be new in terms of the equations, applying the Kirchhoff voltage law, current law, the same procedure, the same analysis that we practiced before, but here we're just gonna consider more advanced form of the electrical circuit that would include these operational amplifiers, and this is what we're gonna discuss the next video. So the objective again of this video is just to give you this introduction, to understand these different keywords, to understand what does it mean amplifiers, especially the operational amplifier. And the next meeting we're gonna do analysis to electrical circuit that include them. Okay, so that's it for this video, and thank you, and see you in the next one.